Something is deeply wrong with the way you think about your own existence. Not philosophically wrong, scientifically wrong. According to some of the most rigorous mathematical models in modern physics, the universe you inhabit, the one filled with galaxies and biology and a 4 billion year story of evolution, may be one of an almost infinite number of universes. And here is where it gets disturbing. In most of those universes, the dominant form of conscious observer is not a civilization. It is not a species that evolved over billions of years. According to the cold logic of thermodynamics and quantum theory, the most common conscious entity in existence may be a single, disembodied, randomly assembled brain that flickered into awareness for a fraction of a second before dissolving back into chaos. There are more of those than there are of us, by an almost incomprehensible margin, which raises one question that physicists genuinely cannot answer. How do you know you are not one of them? Right now, in this moment. Welcome to the most disturbing implication in all of modern cosmology. There is a question that most physicists would rather not answer out loud. Not because the answer is uncertain, not because the mathematics is unfinished, but because the honest answer, the one that follows with cold logical precision from our best scientific models, is so deeply unsettling that it threatens to undermine the very foundation of what science believes about itself. The question is deceptively simple. In a universe as vast as ours, or in the collection of universes that our physics increasingly demands must exist, what kind of conscious observer is most common? You would assume the answer is something like us, something biological, something that spent 4 billion years being sculpted by evolution on a rocky planet orbiting an unremarkable star. Something that crawled out of oceans, developed spines, grew complex nervous systems, built telescopes and particles, accelerators, and eventually found itself sitting here, in this moment, wondering about its own origin. You would assume that consciousness, by its very nature, is the product of a long, ordered, improbable, but ultimately comprehensible chain of physical events. You would assume that we are typical, that we represent what a conscious observer looks like in a universe that permits conscious observers. That assumption is wrong. Not philosophically wrong, not poetically wrong, mathematically wrong. And the way it is wrong is not subtle. When you follow the equations of modern cosmology to their honest conclusions, without softening the result, and without flinching from what the math is actually saying, you arrive at a conclusion that a growing number of serious physicists have spent considerable effort trying to escape. In a universe large enough, or in a collection of universes vast enough, the most common form of conscious observer is not a civilization. It is not a species. It is not even a creature in any ordinary sense of that word. It is a random thermal fluctuation. A spontaneous, accidental, momentary assembly of matter that briefly takes on the configuration of a thinking mind before dissolving back into the surrounding chaos. There are, according to the mathematics, incomparably more of those than there are of us. Not slightly more, not measurably more in any comfortable sense. Incomparably more. By a margin so vast that the total number of human beings who have ever lived, multiplied by the total number of stars in the observable universe, would not even register as a rounding error in the ratio. This is not a thought experiment. It is not a rhetorical device designed to provoke existential unease. It is a genuine, technical, actively debated problem sitting at the center of modern cosmology. It has a name, the Boltzmann brain problem. And it exists not because physicists went looking for trouble, but because two entirely separate and enormously successful branches of physics, each following their own evidence along their own mathematical paths, arrived independently at the conclusion that our universe may be only one of an effectively infinite number of universes. And in an effectively infinite cosmos, the question of what kind of observer is most common becomes one of the most urgent and most disturbing questions that science has ever been forced to take seriously. To understand the full weight of this problem, to feel it not just as an abstract puzzle, but as the genuine scientific crisis it represents, we have to understand first why the multiverse is not science fiction. The word multiverse entered popular culture through comic books and blockbuster films, through stories of heroes slipping between alternate realities and villains from parallel timelines. Because of that cultural association, it is easy to dismiss the idea as imagination rather than inference. That would be a serious mistake. The multiverse that physicists debate is not an invention. It is not a creative leap or a speculative indulgence. It is not even, in many cases, something that the physicists who discovered it wanted to find. It is a consequence. A logical, mathematical consequence of taking our best descriptions of physical reality seriously and following them further than is comfortable. Two paths in physics lead to the multiverse. The first runs through cosmology, through the study of how our universe began and how space itself has evolved over the 13.8 billion years since the Big Bang. The second runs through quantum mechanics, through the study of how matter and energy behave at the smallest conceivable scales, where the rules of ordinary experience do not merely bend, but shatter entirely, and where the concept of a single definite objective reality becomes mathematically questionable in ways that nobody fully anticipated. These two paths were built by different people using different tools for different reasons. Neither one was designed to produce a multiverse, but both did. And together they generate an observer problem so severe that no amount of philosophical discomfort can neutralize its force. Before we walk either of those paths, we need to sit with the problem they produce, because the problem is the point. The problem is what changes how you see everything that follows. Physics, at its deepest level, is built on a practice called inference to the best explanation. You observe something. You construct a theory that accounts for your observation. You test the theory against further observations. If the theory holds, you trust it. You trust it to describe not just what you have already seen, but what you would see if you looked somewhere new or measured something you have never measured before. This is the engine of scientific progress, and it has worked with extraordinary success for several centuries. But it works only because it rests on an assumption that is so fundamental it is almost never stated explicitly. The assumption that the observer doing the observing is a reliable one, that the observations being made are genuine, that the memories of past experiments encoded in the observer's brain correspond to events that actually occurred, that the instruments being used are recording something real, that the entire apparatus of scientific reasoning is being operated by an entity that is genuinely embedded in the physical world it is trying to describe. All of that depends on one foundational premise, that you are the kind of observer you believe yourself to be. An observer with a genuine past. An observer whose memories were formed by real events unfolding in real time. An observer whose brain developed through a long, continuous physical process and whose sensory experience of the world corresponds to something that is actually out there. The Boltzmann brain problem attacks that premise with the full force of thermodynamics. And thermodynamics, unlike philosophy, does not deal in opinions. Ludwig Boltzmann was one of the great architects of 19th century physics. Austrian by birth, brilliant by any measure, and tragically underappreciated in his own time to a degree that contributed to his death by suicide in 1906. He developed statistical mechanics, the framework that bridges the microscopic world of atoms and molecules to the macroscopic world of temperature, heat, and pressure that we experience directly. He gave entropy its rigorous mathematical definition. Entropy, in Boltzmann's formulation, is a measure of the number of distinct microscopic arrangements of a system that correspond to a given macroscopic state. A highly ordered state, such as all the air molecules in a room clustering tightly in one corner, corresponds to a very small number of microscopic arrangements, and therefore has very low entropy. A disordered state, such as those same molecules distributed uniformly throughout the room, corresponds to an astronomically larger number of arrangements, and therefore has very high entropy. The second law of thermodynamics states that entropy in a closed system almost always increases over time, not because of any mysterious directing force, but purely because disordered arrangements so vastly outnumber ordered ones that random physical processes are statistically overwhelmingly likely to produce disorder rather than order. Boltzmann understood, however, that this was a statistical rule rather than an absolute one. In a system of particles evolving randomly over a sufficiently long period of time, entropy does not just march relentlessly upward, it fluctuates. The overwhelming majority of fluctuations are small, brief, and inconsequential, but occasionally, given enough time, a fluctuation will be large, extraordinarily large enough to spontaneously produce a significant pocket of order in the middle of an ocean of chaos. The longer the system runs, the more extreme the fluctuations that will eventually appear. Now, push this logic to its limit. Imagine a universe that has been running not for 14 billion years, but for a number of years so incomprehensibly large that no human notation system can accommodate it. A universe that has long since exhausted its supply of stars, its galaxies, its black holes. A universe that has settled into a state of near maximum entropy, cold and dark, and nearly featureless in all directions. In this condition, almost nothing happens. The universe sits in something close to thermodynamic equilibrium. But quantum mechanics will not permit absolute stillness. Even in a state of maximum entropy, quantum fluctuations continue at the most fundamental level. Virtual particles flicker into and out of existence. Energy oscillates. Fields vibrate at scales too small to observe. And given an eternity of time in which these fluctuations continue accumulating, the probability of any specific configuration of matter assembling itself by pure chance, no matter how elaborate that configuration might be, rises from negligibly small toward statistically inevitable, including the configuration of a functioning brain. Not a brain that grew inside a skull on a rocky planet. Not a brain that was nourished by blood and oxygen and connected to a nervous system shaped by billions of years of natural selection. Just a brain. A spontaneous, random, temporary assembly of atoms that happens purely by the coincidence of a thermal fluctuation to be configured in precisely the arrangement required to sustain a moment of subjective conscious experience. This brain has no true history. It did not come from anywhere. It appeared, perhaps a fraction of a second ago, out of the surrounding chaos. But it may contain within its physical structure something that functions exactly like memories. It may encode information that presents itself to whatever is experiencing it as a lifetime of continuous experience. Those apparent memories were not formed by living through events. They are simply part of the random physical pattern that flickered into existence. The brain experiences what feels like a coherent life in what feels like a real and stable world, and then it dissolves back into the equilibrium from which it came. This is a Boltzmann brain. And the reason it represents a genuine crisis for modern cosmology, rather than merely an interesting philosophical curiosity, can be stated very directly. Consider everything that was required to produce an observer like you. Your existence demanded a universe that began in a state of extraordinarily low entropy, an initial condition so improbable that the physicist Roger Penrose estimated the probability of the Big Bang producing the ordered starting state we observe at approximately 1 part in 10 raised to the power of 10 raised to the power of 123. That universe then had to expand at a rate precisely calibrated to allow the formation of large-scale structure. Hydrogen atoms had to coalesce under gravitational attraction into the first generation of stars. Those stars had to undergo nuclear fusion in their cores, building up heavier elements from the simplest raw materials. Those stars had to die, many of them in violent supernova explosions, scattering the carbon and oxygen and iron and all the other elements that complex chemistry requires across interstellar space. New generations of stars had to form from that enriched gas, often accompanied by planetary systems. On at least one of those planets, the chemical environment had to be suitable for the emergence of self-replicating molecules. Those molecules had to survive and diversify and compete over billions of years through the process of natural selection, assembling organisms of increasing complexity, and eventually producing nervous systems elaborate enough to sustain genuine awareness. And then, that aware organism had to develop language, culture, abstract reasoning, and scientific methodology sophisticated enough to begin asking coherent questions about the physical laws governing its own existence. Every single step in that sequence is improbable in isolation. The entire sequence, considered as a unit, carries a probability so small that it makes winning a lottery every day for 1,000 years look unremarkable. The ordered chain of events connecting the Big Bang to a conscious human observer is one of the most improbable outcomes that the laws of physics permit. A Boltzmann brain requires precisely none of that. It requires only time and the quantum jitter of matter in thermal equilibrium. No low entropy beginning, no star formation, no planetary chemistry, no biology, no evolution, just the endless patient accumulation of random fluctuations over an eternity, until one of them happens to assemble the right configuration. And while the probability of any given fluctuation producing a brain is extraordinarily small in absolute terms, it is incomparably larger than the probability of the entire ordered sequence of cosmic and biological events that produced you. When you compare the two probabilities honestly, the ratio is not a few orders of magnitude. It is not even a number that can be meaningfully written down. The probability that a given moment of conscious experience arises from a random fluctuation, rather than from evolved, embodied cognition, is so much larger that it belongs to a different mathematical universe of comparison. This is why physicists like Don Page, Sean Carroll, Andreas Albrecht, and others have written serious academic papers treating the Boltzmann brain problem not as an amusing paradox, but as an urgent empirical threat to the internal consistency of our cosmological models. Their argument is precise and devastating. If your theory of the universe predicts that Boltzmann brains vastly outnumber evolved observers, then your theory has generated a prediction that directly contradicts the most fundamental observation available to any scientist. The observation that the scientist doing the observing is an evolved observer rather than a random fluctuation. A theory that predicts you should almost certainly not exist as the kind of observer you appear to be is a theory that is in deep and possibly fatal trouble. But here is what makes this more than a technical problem for theorists to resolve among themselves. Here's what makes it touch something genuinely disorienting. If the multiverse is real, and if the physics of thermal fluctuations applies across its full extent, then you cannot rule out the possibility that you are a Boltzmann brain on the basis of your experience. Because a Boltzmann brain would have an experience indistinguishable from yours. It would seem to remember a childhood. It would seem to have a body. It would seem to be surrounded by a stable, physical world operating according to consistent laws. It would seem to have observed experiments and accumulated knowledge and developed confident beliefs about the nature of reality. Every single feature of your experience that you might point to as evidence that you are a real, embedded, evolved observer would also be present in the experience of a Boltzmann brain that flickered into existence 1 second ago. There is no internal test. There is no observation you can make from within your own experience that would distinguish genuine embeddedness from random fluctuation. How do you know you are not that right now? This question is not asked here to induce anxiety. It is asked because it is the question that cosmologists are genuinely and seriously confronted with when they follow their own theories to their natural conclusions. It is asked because the honest answer is that we cannot be certain. And the fact that we cannot be certain, combined with the mathematical argument that Boltzmann brains should vastly outnumber observers like us, creates a problem that cuts to the very core of what science is and how it works. Science is not just a collection of theories, it is a practice, it is a method. And that method depends, at every step, on the assumption that the observations being used to test theories are reliable, that the data collected in laboratories over centuries corresponds to something real, that the memories and records and measurements accumulated by generations of scientists encode genuine information about a genuine physical world. If those observations were generated by a random fluctuation, they are not reliable. They are noise. They prove nothing. They confirm nothing. They refute nothing. The Boltzmann brain problem does not merely raise doubts about whether our universe had a beginning, or whether other universes exist, or whether the constants of nature could have been different. It raises doubts about whether the entire enterprise of observational science is in principle capable of learning anything real. It is a problem that, if not resolved, undermines physics from the inside. And the tragedy is that the problem was not created by carelessness or speculation. It was created by rigor. By following the most successful physical theories we have to the places they logically lead. The multiverse is one of those places. And in that place, the most common observer is not a scientist looking through a telescope. It is a momentary flicker of accidental awareness, dissolving before it can take a second measurement. Understanding why the multiverse is so compelling to physicists, and why it generates this observer crisis so unavoidably, requires us to examine the two great pathways that lead there. The first pathway runs through the story of how space itself was born and what happened in the first fraction of a second of cosmic time. It is a story involving a process called inflation, and a consequence of that process called eternal inflation, and a landscape of possibility so vast that the word universe no longer does justice to what the equations describe. The second pathway runs through the foundations of quantum mechanics, and a radical proposal made by a graduate student in 1957 that the wave function never collapses, that every quantum event plays out every possible way simultaneously, and that the entirety of reality is therefore a constantly branching tree of diverging histories, each one as real as every other. Both pathways are scientifically serious. Both are supported by evidence, by mathematical consistency, and by the testimony of physicists who did not set out to find them, but were led there by the logic of their own work. And both, when examined carefully, amplify the Boltzmann brain crisis in ways that reinforce rather than cancel each other. You are, in this moment, sitting inside what feels like a coherent and continuous reality. The world around you appears stable. Your memory of the past appears reliable. Your expectations about the next few minutes feel well-grounded. Nor of that rests on the assumption that you are a particular kind of observer. An observer with a genuine history, embedded in a genuine physical world, whose experience of reality corresponds to something that is actually there. The deepest and most honest question that modern cosmology is currently wrestling with is whether that assumption can be justified. Whether the theories that explain our universe so successfully are also theories that undermine our ability to trust any observation at all. That question is not resolved. It is not close to being resolved, but it is real. It is mathematically precise, and it is the question that everything else that follows is built around. The physics of how the multiverse was built, how it multiplies observers beyond any manageable count, and what that means for every measurement ever made, begins with the story of the first extraordinary fraction of a second after the beginning of everything we can see. Part 2. The Inflationary Multiverse. How physics accidentally built infinite universes. In the winter of 1979, a young postdoctoral physicist named Alan Guth was working late in his office at the Stanford Linear Accelerator Center, wrestling with a problem that had been nagging at cosmology for years. The problem was not exotic. It was not the kind of question that sounds glamorous in a popular science article. It was, in the language of working physicists, a fine-tuning problem. A question about why the universe we observe looks the way it does, when the equations that govern its behavior suggest it had every reason to look entirely different. The Big Bang model, by that point, was firmly established. The expansion of the universe had been observed and confirmed. The cosmic microwave background radiation The faint afterglow of the primordial fireball had been detected in 1964 by Arno Penzias and Robert Wilson. The abundance of light elements like hydrogen and helium matched the predictions of nucleosynthesis theory with remarkable precision. The broad outline of cosmic history, from an unimaginably hot and dense beginning to the cooler, more diffuse universe we inhabit today, was not seriously disputed. But several features of that universe resisted comfortable explanation. The first was the flatness problem. The geometry of the universe, as measured by how matter and energy curve the fabric of space-time, appears to be extraordinarily close to perfectly flat. Not slightly flat, not approximately flat in some loose observational sense. Flat to a degree that, when you trace the equations backward in time toward the Big Bang, demands that the initial conditions of the universe were fine-tuned to a precision of better than 1 part in 10 to the 60th power. Even the smallest deviation from exact flatness in those first moments would have produced a universe that either collapsed back on itself almost immediately or expanded so rapidly that no structure of any kind could ever have formed. Either way, we would not be here. The universe we observe is balanced on a knife edge so razor thin that calling it a coincidence feels like a profound abdication of scientific responsibility. The second problem was the horizon problem. When we measure the temperature of the cosmic microwave background radiation in different directions across the sky, it is the same everywhere to within about 1 part in 100,000. Every region of the sky, including regions separated by such vast distances that light traveling since the beginning of time could never have crossed from one to the other, has precisely the same thermal history. But in the standard Big Bang model, those regions were never in contact. They never exchanged energy. They never had the opportunity to reach thermal equilibrium with each other. In thermodynamics, you cannot have identical temperatures in regions that have never interacted. It is like finding every room in a building at exactly the same temperature despite the fact that the heating system has never been switched on, and no room has ever been connected to any other. The standard Big Bang model had no explanation for either of these observations. They required that the initial conditions of the universe were set with a precision so extraordinary that the word coincidence stopped being a scientific answer and became an embarrassing placeholder. Something was missing from the theory. What Guth found in that late-night calculation in 1979 was a mechanism that solved both problems simultaneously with one stroke. He proposed that in the first extraordinary fraction of a second after the Big Bang, before the universe was even 1 billionth of 1 billionth of 1 billionth of a second old, space underwent a period of exponential expansion of almost inconceivable rapidity. Not the gradual, decelerating expansion that the universe undergoes today under the competing influences of gravity and dark energy. Something incomparably more violent. A period during which the universe doubled in size not once, not 10 times, but somewhere in the neighborhood of 100 times in a window of time so brief that no unit of human measurement comes close to capturing it. Guth called this process inflation. The mechanism driving inflation, in Guth's original model, was a hypothetical energy field now called the inflaton field, occupying a high-energy metastable state. This field carried with it a kind of negative pressure, a repulsive gravitational effect that caused space itself to expand at an exponential rate. Think of it not as matter flying outward through pre-existing space, but as the fabric of space itself stretching, every point moving away from every other point at a rate that grew faster the further apart they were. The expansion was so rapid that regions which had initially been in thermal contact, sharing energy and reaching equilibrium, were suddenly separated by distances so vast that light could never bridge the gap between them. The smoothness of the cosmic microwave background is therefore not a coincidence. It is a relic, a memory of the brief window before inflation began, when the universe was small enough for its different regions to have communicated, stretched across the sky by the violence of the expansion that followed. The flatness problem dissolves equally elegantly. Imagine the surface of a balloon. If you look at a small section of a partially inflated balloon, its curvature is obvious. It is clearly a curved surface, but if you inflate that balloon to the size of the Earth, any patch small enough for you to examine directly will appear, to extraordinary precision, to be flat. The curvature is still there in principle, but it has been stretched across a scale so vast that it becomes unmeasurable from any local vantage point. Inflation performed exactly this operation on the geometry of space-time. Whatever initial curvature the universe possessed before inflation, the extraordinary expansion diluted it to a level indistinguishable from zero within any observable region. The flatness we measure today is not a miraculous initial condition. It is a natural, almost unavoidable consequence of the inflationary mechanism. Guth's paper, published in 1981, was received with immediate and widespread recognition by the cosmological community. It did not merely patch the problems it addressed. It addressed them in a way that felt physically natural, that arose from a coherent theoretical mechanism, rather than from an ad hoc adjustment to the initial conditions. Within a few years, the inflationary model had been refined and extended by a number of physicists, most notably Andrei Linde at the Lebedev Physical Institute in Moscow, and independently by Andreas Albrecht and Paul Steinhardt. They addressed a technical flaw in Guth's original model and produced what is now called new inflation, a smoother and more physically consistent version of the basic idea. But it was Linde who pushed the inflationary framework to a place that nobody, including Guth, had fully anticipated. Beginning in 1983 with his development of chaotic inflation, and continuing through the mid-1980s, Linde built the case for a concept that would reshape cosmology's understanding of reality at the largest conceivable scale. He called it eternal inflation, and the implication it carried was precisely the one encoded in its name. Inflation, once started, never fully stops. Here is why. In the inflationary model, the inflaton field is not a perfectly uniform entity distributed identically across all of space. At the quantum level, it undergoes fluctuations, small random perturbations. These fluctuations are not a design flaw or an imprecision in the theory. They are a fundamental, inescapable consequence of quantum mechanics applied to any field existing in physical space. The Heisenberg uncertainty principle forbids perfect stillness at the quantum level. Everything fluctuates, always. Now consider what these quantum fluctuations mean for the inflationary process itself. Inflation is driven by the inflaton field slowly rolling down a potential energy landscape, like a ball rolling down a hill from a high energy starting position toward a lower energy final state. When the field reaches the low energy end of the landscape, inflation ends. The energy stored in the field is converted into the hot, dense plasma of particles that we recognize as the beginning of the conventional Big Bang. Stars, galaxies, chemistry, and eventually biology can follow. But quantum fluctuations can kick the field back up the hill. Randomly, spontaneously, in individual regions of space, quantum jitter can push the inflaton field to higher energy rather than lower, extending the inflationary process in that region rather than terminating it. And here is the critical point. Because the universe is expanding exponentially during inflation, the regions where inflation continues grow far faster than the regions where it ends. Space is being created faster than it is being converted into ordinary matter. The inflationary process does not terminate globally. It terminates locally in isolated patches while continuing everywhere else. Each patch where inflation ends becomes a bubble, a region of space that settles into a lower energy state and evolves according to the physics of the conventional Big Bang. Each such bubble is, in effect, a universe. Our universe, most likely, is one such bubble. But the inflationary process that generated our bubble did not stop when our bubble formed. It continues outside our bubble, in the wider inflationary space-time that surrounds us, constantly generating new bubbles, each one a separate universe with its own physical history, potentially its own physical constants, its own particle masses, its own laws governing the behavior of matter and energy. And because the inflationary background grows faster than bubbles form within it, the total number of bubble universes does not converge towards some finite limit. It grows without bound, eternally. The multiverse in this picture is not merely large, it is infinite in a way that should be taken with full mathematical seriousness. Not approximately infinite. Not very large in some poetic sense. Genuinely, formally, mathematically without end. Linda's eternal inflation was not merely a theoretical curiosity. It emerged naturally and almost inevitably from the same mathematical framework that solved the flatness and horizon problems. If you accepted inflation as the explanation for those observational successes, and the evidence for inflation had become increasingly strong, then you were accepting a mechanism that, when quantum mechanics was applied to it honestly, produced eternal inflation as a near unavoidable consequence. You could not have the benefits of inflation without accepting that inflation was almost certainly eternal. The multiverse came packaged with the solution to the universe's most troubling fine-tuning problems. The implications for the constants of nature are equally profound. In Guth's original model, there was an implicit assumption that the laws of physics were the same everywhere, that different bubble universes would share the same particle masses, the same fundamental forces, the same physical constants. But the development of string theory in the 1980s and 1990s suggested a different picture. String theory, the leading candidate for a unified theory of all fundamental forces, does not predict a unique set of physical laws. Instead, it produces what string theorists call the landscape, an almost incomprehensible number of distinct possible configurations of physical law, each corresponding to a different vacuum state of the underlying theory. Estimates of the number of distinct possible vacua in the string theory landscape run to 10 raised to the power of 500. Each vacuum corresponds to a different universe with different particle masses, different coupling constants, different numbers of effective spatial dimensions, different values for the cosmological constant. When you combine the string theory landscape with eternal inflation, you get a picture in which the different bubble universes generated by the eternal inflationary process are not merely separate regions of space, but distinct physical realities, each obeying its own version of the laws of nature. Most of those universes, by any reasonable estimate, are hostile to anything resembling the complexity required for life. Their constants are tuned to values that do not permit atoms to form, or that cause any structure that forms to immediately collapse under gravity, or that result in a cosmological constant so large that space expands before galaxies can assemble. Life-permitting universes like ours occupy a tiny and rarefied corner of the landscape. We exist in one of those rare corners not because the laws of physics were designed with us in mind, but because we could not find ourselves in any other kind. That argument, the anthropic argument, will demand its own careful examination. But for now, the relevant point is simpler and more disturbing. An infinite multiverse containing every possible combination of physical constants does not merely contain a large number of life-permitting universes, it contains an infinite number of them. And within each life-permitting universe, the inflationary process stretched the initial quantum fluctuations of the inflaton field across cosmological scales, seeding the density variations that eventually grew into galaxies and stars and planets, and the biology that unfolds on them. But that same inflationary mechanism also operated in regions that were far from life-permitting. The vast majority of the multiverse, by every measure available, is not like our universe. It is not ordered. It is not structured. It is not populated by the elaborate chemistry and biology that characterizes our corner of existence. And yet, it exists. And in its existence, it contains something that is deeply troubling when combined with what thermodynamics tells us about the behavior of matter in the far future of any region that manages to persist long enough. Remember what Boltzmann taught us. In a system evolving over a sufficiently long time, thermal fluctuations will occasionally produce improbable states. The longer the system runs and the larger its volume, the more extreme the fluctuations that will inevitably appear. Now, consider the inflationary multiverse in its full extent, an effectively infinite volume of space containing an effectively infinite number of bubble universes, each one evolving through its own cycle of star formation and stellar death, each one heading over timescales of inconceivable length toward a state of high entropy, cold, dark, nearly featureless equilibrium. And in that equilibrium state, quantum fluctuations continue. They have no choice. Quantum mechanics does not permit complete stillness. And given infinite time and infinite volume across which fluctuations can occur, the probability of any specific configuration of matter assembling itself spontaneously, including the configuration of a functioning conscious brain, is not merely possible. It is, in the most rigorous statistical sense, certain. Not once, not a finite number of times, an infinite number of times distributed across the infinite extent of the eternal inflationary multiverse. Now place that infinite population of randomly fluctuating Boltzmann brains alongside the total population of evolved observers in the same multiverse. The evolved observers, despite existing in every life-permitting bubble universe across the infinite landscape, are produced by an extraordinarily improbable chain of physical events. Boltzmann brains, by contrast, require only the continued existence of time and the quantum jitter of matter. Their production rate, per unit volume per unit time in the deep future equilibrium state of any long-lived universe, is many orders of magnitude larger than the production rate of evolved observers through biology. And because the equilibrium state of a universe persists for timescales incomparably longer than the brief, bright window of stellar activity during which biology is possible, the total number of Boltzmann brains produced over the full history of even a single bubble universe dwarfs the total number of evolved observers that universe ever contained. Multiply that across an infinite multiverse, and the ratio becomes formally undefined in the usual sense, because both the numerator and the denominator are infinite. But physicists can ask a local version of the question, within any given region of space-time, at any given time after the era of star formation has ended, what fraction of observers are evolved rather than random? The answer, according to the statistical mechanics of thermal fluctuations, applied to the long-term evolution of any low-energy universe, is overwhelming in the wrong direction. Boltzmann brains dominate, massively and irreversibly. This is not a speculative extrapolation. This is what the mathematics of eternal inflation combined with thermodynamic equilibrium actually predicts when followed past the stellar era into the deep future of any long-lived universe. The Boltzmann brain problem is not a philosophical quibble with the inflationary framework. It is a quantitative threat to its self-consistency. And the reason it is a threat, rather than merely an inconvenience, is that it strikes at the one assumption that all of cosmology depends upon. The assumption that the observers doing cosmology are the kind of observers whose reasoning can be trusted. How deep that threat runs, and what it demands of the entire structure of probabilistic reasoning that modern physics is built upon, is where this story must ultimately arrive. What Guth found in that late-night calculation was not merely a solution to the flatness and horizon problems. He found the opening of a door that led, through a sequence of mathematically rigorous steps, to a picture of reality so vast and so strange that the universe visible to our telescopes shrinks to a negligible fraction of what exists. And in that picture, the question of what kind of observer is typical becomes not just unanswerable, but actively threatening to the foundations of cosmological reasoning. The inflationary multiverse did not intend to undermine science. It intended to do science better. It intended to explain observations that the previous framework could not account for. It succeeded in that narrow goal with remarkable thoroughness. The predictions of inflation, including the specific pattern of fluctuations in the cosmic microwave background and the near-perfect flatness of the universe's geometry, have been confirmed by satellite observations of extraordinary precision. The theory is not a guess, It is a framework supported by real data. But the same mathematical machinery that generates those confirmed predictions also generates an infinite multiverse. And that infinite multiverse contains, inevitably, an observer population so dominated by random fluctuations that the typical conscious entity in its full extent is not a physicist writing equations on a chalkboard. It is a ghost, an accident. The disturbing implication of the multiverse is not that other universes exist. It is what their existence, combined with the honest application of thermodynamics, tells us about what kind of observer dominates the full distribution of conscious experience. The inflationary picture does not merely produce a cosmos large enough to contain life, it produces a cosmos old enough and thermodynamically patient enough to produce Boltzmann brains in numbers that dwarf every evolved observer it ever generated through biology. That is not a philosophical footnote. It is the statistical conclusion that the same equations which predict the flatness of our universe and the spectrum of the cosmic microwave background also produce when followed past the era of stars into the vast equilibrium that follows. There is a second pathway to the multiverse, one that arrives from a completely different direction. One that does not invoke cosmic inflation or the thermal equilibration of bubble universes. One that emerges from the mathematical heart of quantum mechanics itself, from the equations that govern the behavior of matter at the smallest conceivable scales. That pathway was opened by a young graduate student at Princeton University in 1957, and it leads to a multiverse so different in character from the inflationary one, and yet so convergent in its implications for the observer problem, that the combined weight of the two is almost impossible to set aside. To understand that second pathway, we have to go somewhere far stranger than the cold equilibrium of a dying universe. We have to go into the structure of quantum reality itself, into the question of what happens when a particle is not in any single definite state, and what the mathematics demands must occur at the moment we try to find out. Hugh Everett III was 26 years old when he submitted the dissertation that would either redefine reality or be quietly buried, depending on who you asked and when you asked them. The year was 1957. Everett was a graduate student at Princeton University, working under the supervision of John Archibald Wheeler, one of the most influential physicists of the 20th century. The man who would later coin the term black hole, and whose thinking about the relationship between observation and physical reality would shape the deepest questions in quantum foundations for decades. Everett had spent years staring at a problem that most of his colleagues preferred to step around. A problem so fundamental that its existence at the very core of quantum mechanics should have been a scandal, but had instead been managed in the physics community by a kind of collective agreement not to look directly at it. The problem was measurement, specifically what happens to the mathematical description of a quantum system at the moment someone observes it. Quantum mechanics, as a computational tool, is the most precisely verified theory in the history of science. Its predictions match experimental results to a degree of accuracy that has no parallel in any other branch of physics. The predictions of quantum electrodynamics, the quantum mechanical description of electromagnetism, have been confirmed to better than 1 part in 1 billion. The theory works. It works so well that dismissing it or replacing it with something more comfortable is simply not an option for any serious physicist. But quantum mechanics contains, at its heart, a structure that produces deep conceptual unease the moment you look at it carefully. That structure is the wave function. In quantum mechanics, the state of any physical system is completely described by its wave function, a mathematical object that encodes not a single definite set of values for physical quantities like position, momentum, and spin, but a superposition of all possible values, weighted by their respective probabilities. An electron does not have a definite position before it is measured. It has a wave function that distributes its presence, mathematically speaking, across a range of possible positions. A particle does not have a definite spin before it is measured. It exists in a superposition of spin up and spin down simultaneously. Both states present in the mathematics with their respective probability weights. This is not an expression of ignorance. It is not the case that the electron really is in one position, but we simply do not know which one. The experimental evidence, culminating in the Bell inequality violation experiments that earned John Clauser, Alan Aspect, and Anton Zeilinger the Nobel Prize in Physics in 2022, confirms beyond any reasonable doubt that quantum superposition is a genuine feature of reality and not merely a reflection of incomplete information. The particle genuinely has no definite position. The spin genuinely has no definite orientation. The wave function is not a summary of what we know. It is a description of what is. And this is where the measurement problem emerges with its full, uncomfortable force. When you actually measure the position of an electron, you get a single definite answer. Not a smeared distribution, not a range of values, one number, one outcome. The wave function, which before the measurement described a superposition of many possible positions, appears to collapse instantaneously into a single sharp spike at the measured value. Or may the other possibilities, all the other terms in the superposition, simply vanish from the mathematical description. This collapse is called wave function collapse, or the reduction of the state vector, and it is the most conceptually problematic step in all of quantum mechanics. It is problematic for a precise and unavoidable reason. The Schrödinger equation, the fundamental equation of motion in quantum mechanics, the equation that governs how wave functions evolve over time, is perfectly linear and perfectly deterministic. It never produces collapse. It never singles out one outcome from a superposition. It evolves superpositions smoothly and continuously, always preserving the coexistence of all the terms. A wave function that starts as a superposition remains a superposition under the Schrödinger equation, forever. The two halves of quantum mechanics are therefore in direct contradiction. The Schrödinger equation says the superposition continues. The measurement rule says it collapses. The theory contains within itself two incompatible dynamical rules, and it applies them in different contexts without providing any principled account of what distinguishes those contexts, or why one rule applies rather than the other. The standard interpretation developed primarily by Niels Bohr and his colleagues in Copenhagen in the 1920s and 1930s manages this contradiction by decree. It simply asserts that measurement causes collapse. It does not explain what a measurement is in physical terms. It does not specify what makes a measuring device different from any other collection of atoms. It does not derive collapse from any deeper principle. It simply declares that when an observation is made, the wave function collapses, and it prohibits questions about what the process of collapse actually consists of. As Bohr himself suggested, the right approach was to use quantum mechanics as a calculating tool and not ask what it means. For most working physicists, this approach was entirely satisfactory. The theory gave correct answers. It allowed them to build transistors and lasers and medical imaging technology. Why demand more? Why risk the productivity of an entire field by insisting on a metaphysical account of what observation actually does? Hugh Everett looked at this situation and saw something that his contemporaries largely did not. He saw that the Copenhagen Decree was not merely philosophically unsatisfying, it was physically incomplete in a way that mattered. Specifically, it required the existence of a classical realm, a macroscopic world operating by classical rules, to serve as the stage on which measurements were performed, while simultaneously insisting that everything in the classical realm was made of quantum particles governed by the Schrödinger equation. The theory required the existence of something outside of quantum mechanics in order to make quantum mechanics work. It bootstrapped its own completeness by assuming what it needed to explain. Everett decided to remove the assumption entirely. He proposed taking the Schrödinger equation with complete, uncompromising seriousness as the sole and universal equation of motion for all physical systems, without exception. If the Schrödinger equation says a superposition continues, then it continues. Always. without exception, including during measurement. There is no collapse. There is no special rule for observation. There is only the wave function, evolving according to the Schrödinger equation forever. But if the wave function never collapses, then what happens during a measurement? If an electron in a superposition of spin up and spin down interacts with a measuring device, and the Schrödinger equation governs the entire interaction, then the measuring device itself enters a superposition. There is a branch of the wave function in which the device registers spin up, and a branch in which it registers spin down. Both branches continue to exist in the mathematics, because the Schrödinger equation does not eliminate them. If the device is then read by a human observer, the observer also enters a superposition. There is a branch of the wave function in which the observer sees spin up, and a branch in which the observer sees spin down. Both observers exist in the mathematics. Both are real in the only sense that matters within the theory, which is that both are described by the wave function. This is the many worlds interpretation. Every quantum measurement, every quantum event with multiple possible outcomes does not select one outcome and discard the others. It produces all outcomes, each in its own branch of the universal wave function, each branch going on to evolve independently according to the Schrödinger equation, each branch containing its own version of the measuring device, the observer, the laboratory, the planet, the galaxy, and everything else entangled in the measurement chain. Wheeler, Everett's supervisor, was initially sympathetic to the idea, but deeply concerned about its reception. He arranged for Everett to visit Copenhagen and present the idea to Bohr, hoping to secure the approval of the founding figure of quantum interpretation. The meeting was not a success. Bohr and his colleagues found Everett's proposal deeply unsatisfying. The idea was revised, condensed, and eventually published in a shortened form in the journal Reviews of Modern Physics in 1957. It attracted little attention. Everett, disappointed by the reception, left academic physics shortly afterward and spent his career working in defense consulting. He died in 1982 at the age of 51 and did not live to see his idea eventually rehabilitated into one of the most seriously discussed interpretations in the foundations of quantum mechanics. Today, the many worlds interpretation, also called the Everett interpretation or relative state formulation, has a substantial and growing constituency among physicists who think carefully about the foundations of the theory. Proponents include David Deutsch at Oxford, one of the pioneers of quantum computing, who has argued that quantum computation provides strong empirical evidence for the reality of parallel branches, and Sean Carroll at Johns Hopkins, who has written extensively about the many worlds picture as both the most mathematically natural and the most scientifically honest reading of quantum mechanics. The interpretation is not universally accepted, and significant debates continue about how to derive the probability rule of quantum mechanics within the many worlds framework. But it is no longer a fringe curiosity. It is a live scientific option taken seriously by serious people. What the many worlds interpretation implies about the structure of reality is staggering in its scope. Consider how many quantum events occur in the observable universe every second. Radioactive decays, photon absorptions and emissions, electron transitions, quantum tunneling events, thermal fluctuations at the atomic scale, chemical reactions in living cells, neural firing events in every brain on every planet. Each one of these events involves quantum systems with multiple possible outcomes. Each one, according to the many worlds interpretation, produces a branching of the universal wave function. Each branch goes on to generate its own subsequent quantum events, each of which branches again and again and again in an exponentially expanding tree of diverging realities. The number of branches that exist at this moment, right now, in the universal wave function, is not merely large. It is a number so far beyond any quantity that human intuition can process, that comparisons to the number of atoms in the observable universe, or the number of possible chess games, serve only to illustrate how inadequate such comparisons are. The branching rate, Across the full volume of the observable universe, operating at the quantum level where events occur at timescales measured in fractions of a second, produces a proliferation of distinct reality branches that compounds continuously and without any theoretical upper bound. And every single one of those branches is, according to the theory, equally real. Now, consider what this means for the observer problem. Inflation had already confronted us with a disturbing numerical imbalance between Boltzmann brains and evolved observers distributed across an infinite landscape of bubble universes. The many worlds interpretation compounds that problem in a completely independent direction. It does not merely multiply the number of universes across cosmic space, it multiplies the number of reality branches across quantum probability space, moment by moment, in every cubic centimeter of every existing universe. The total observer count in the many worlds multiverse does not merely exceed any manageable number. It exceeds any number that could be generated by the inflationary multiverse acting alone, because the branching occurs not at the scale of cosmological bubble formation, but at the scale of individual quantum events, everywhere, continuously, in branches where physics permits life to evolve, which is the only kind of branch in which there is anyone to ask these questions. Every conscious observer exists not in one unique continuous experience, but in a constantly bifurcating river of nearly identical copies, each flowing into a slightly different future with every quantum event that occurs in or near their bodies or their environment. Your decision to continue watching rather than stopping a moment ago did not eliminate the branch in which you stopped. Both exist. Both contain an observer who believes they made the only choice available to them. Neither is less real than the other in the mathematics of the theory. But here is where the many worlds interpretation sharpens the observer problem in its own distinctive way. Probability. In ordinary quantum mechanics, the wave function assigns probability amplitudes to different outcomes, and the squared magnitude of those amplitudes gives the probability of each outcome occurring upon measurement. In the Copenhagen interpretation, this probability rule, called the Born rule, is simply postulated as part of the measurement axiom. It is a foundational assumption whose justification lies in its agreement with experiment, rather than in any derivation from deeper principles. In the many worlds interpretation, there is no collapse, which means there is no measurement axiom, which means the Born rule cannot be postulated in the same way. If every outcome of every quantum measurement actually occurs in some branch, then in what sense is any branch more or less probable than another? If you flip a quantum coin and both heads and tails occur in separate branches, what does it mean to say that heads has a probability of 1/2? Both happen. Both branches exist. From the perspective of each branch, the coin landed definitively. There is no unactualized possibility. There is no outcome that was not realized somewhere. David Deutsch and later David Wallace have proposed derivations of the Born rule from decision theory within the many worlds framework, arguing that a rational agent who knows they're about to branch should assign decision theoretic weights to outcomes that match the Born rule probabilities. These arguments are ingenious and have been influential, but they remain controversial. Critics argue that they smuggle in probabilistic assumptions through the back door, or that they conflate the rational weighting of outcomes with the physical frequency of their occurrence. The debate is unresolved. What is clear is that the many worlds interpretation does not make reasoning about probability straightforward. In a reality of infinite quantum branches, asking what is probable becomes deeply problematic because probability requires a denominator, a total count of trials or possibilities, and in an infinite branching structure, that denominator is not well defined by ordinary means. The same measure problem that afflicts eternal inflation, the question of how to count observers meaningfully in an infinite space, reappears here in the quantum context with equal force and equal intractability. And when you combine the two multiverses, the inflationary one generating infinite bubble universes across cosmic space, and the quantum one generating infinite branches within each of those bubble universes, the observer count that results is of a kind that makes the Boltzmann brain problem not merely difficult, but potentially inescapable from within the framework of contemporary physics. Boltzmann brains can appear in quantum branches too. A quantum fluctuation on a sufficiently extreme scale, while exponentially improbable in any given branch, will occur with certainty somewhere in the infinite branching structure. The same statistical argument that produces Boltzmann brains in the thermal equilibrium of a long-lived universe operates in the many worlds context as well, distributing random conscious fluctuations across the infinite tree of quantum reality. There is a further dimension to the many worlds picture that is worth examining carefully, because it touches on something that the inflationary multiverse alone does not address. In the inflationary multiverse, the different bubble universes are causally disconnected. Nothing that happens in one bubble can influence anything in another. They are, in the most rigorous physical sense, separate realities. The observer in one bubble has no access, even in principle, to the observers in any other bubble. But in the many worlds interpretation, all branches of the universal wave function are, in a formal mathematical sense, part of the same physical system. They are not separate realities in the way that bubble universes are separate. They are branches of one universal wave function, evolving according to one equation. This means that in the many worlds picture, the question of which branch you are in is a question about your relationship to the universal wave function, not about which of several disconnected realities you happen to inhabit. And the disturbing aspect of this is that there is no physical fact about the universe that selects your branch as the real one. All branches are equally real in the formalism. The branch you are in is not more real than the branch in which you made a different decision, or the branch in which your heart stopped this morning, or the branch in which the Earth was struck by a large asteroid last year. All of those branches exist right now, in the mathematics that describes reality. Your particular branch has no special status. You did not arrive here by winning a cosmic lottery. You arrived here simply because your experience has to be somewhere in the tree, and this is where it is. This connects back to the core disturbing implication with which we began. In the many worlds multiverse, every quantum event that could have produced a conscious observer does produce one, in some branch, including events that have nothing to do with biology. The many worlds interpretation does not merely multiply the number of universes across cosmic space. It multiplies observer-generating events across quantum probability space, moment by moment, everywhere. And among those events are quantum fluctuations extreme enough to produce Boltzmann brains in individual branches of the universal wave function. The same statistical argument that generates them in the thermal equilibrium of a long-lived universe operates here too, now distributed across an infinite branching tree rather than across the equilibrium of a single dying cosmos. These branches exist. They are part of the universal wave function. The observers they contain are real in the same sense that any Everettian observer is real, and there are, by every measure available to us, incomparably more of those branches than there are branches containing observers embedded in evolved, biologically continuous conscious lives. The many worlds interpretation was never designed to produce this conclusion. Everett's goal was modest and mathematically precise. He wanted to remove the measurement postulate from quantum mechanics and show that the theory was self-contained without it. He succeeded in that goal. But the cost of that success, paid not by Everett but by anyone who takes his interpretation seriously and follows its implications honestly, is a picture of reality in which the evolved, biologically embedded observer is a statistical rarity in the full space of conscious experience. We have now traced two independent scientific pathways to the same destination, arriving there from opposite directions. Eternal inflation arrives through the large-scale architecture of the cosmos. Many worlds arrives through the quantum structure of every measurement ever made. They converge on the same accounting problem. An effectively infinite multiverse of bubble universes, each one internally branching at every quantum event, generates an observer population so vast and so dominated by statistical accidents that the question of what kind of observer is typical is no longer a philosophical puzzle. It is a mathematical emergency. And it is an emergency that a third framework, one built specifically to explain why observers like us exist at all, was supposed to resolve. What that framework actually does to the problem is something far more uncomfortable than resolution. This finding would be merely disturbing if it had no implications for how we practice science, but it does have such implications, profound and direct ones. Because the apparatus of scientific reasoning is not separable from the observer doing the reasoning, science is what conscious observers do. And if our best theories of physics tell us that most conscious observers cannot be trusted to be reporting on a real world, that their memories are not formed by real events and their measurements are not recording real phenomena, then those theories are not merely producing a strange metaphysical conclusion. They are threatening to undermine their own evidential base. To understand how this threat unfolds, and to understand why it is taken seriously rather than dismissed, we need to examine the tool that physicists most commonly deploy to explain why observers like us exist at all. We need to understand the anthropic principle, what it can and cannot do, and why, applied honestly within the multiverse framework, it sharpens the Boltzmann brain problem rather than dissolving it. That examination requires us to think carefully about a concept that sounds almost circular the first time you hear it. The idea that the universe we observe must be compatible with our existence simply because we are here to observe it. That idea is more powerful and more dangerous than it initially appears. It is both the primary tool physicists use to make sense of the multiverse's fine-tuned constants, and the primary reason that same multiverse struggles to explain why we are the kind of observers we seem to be. The anthropic principle is a filter. And like all filters, it is defined not just by what it lets through, but by what it keeps out. Understanding what it keeps out and what it inadvertently allows in is the key to understanding why the observer problem at the heart of multiverse cosmology is so resistant to easy resolution. There is a style of reasoning in physics that feels, the first time you encounter it, like cheating. It arrives dressed in the language of logic and wears the respectable clothing of probability theory. But something about it sets off an instinctive alarm in the minds of scientists trained to derive conclusions from evidence rather than from the mere fact of their own survival. That reasoning is the anthropic principle, and despite the discomfort it provokes, despite the accusations of circularity and the suspicion that it explains nothing while appearing to explain everything, it has become one of the most frequently invoked frameworks in modern cosmology. It is used to address the most stubborn, fine-tuning problems in physics. It is used to make sense of the multiverse's staggering range of possible physical constants. And it is used, with varying degrees of success, to explain why the universe we find ourselves in permits the existence of beings capable of asking why. The basic idea is almost embarrassingly simple when stated directly. We can only observe a universe that is compatible with our existence as observers. This sounds trivially obvious. Of course, we can only be in a universe where we can be. What else could be true? But the simplicity of the statement conceals a genuine and powerful logical content, because it functions as a selection effect. It tells us that the act of observation is not a neutral sampling of all possible universes. It is a biased sampling, filtered by the requirement that the observer exists. And that filter, applied carefully, can explain why we observe features of the universe that would otherwise seem to require miraculous fine-tuning. Consider the cosmological constant, the energy density of empty space, which Einstein introduced into his equations of general relativity and later called his greatest blunder before it was observationally confirmed in 1998, to be not zero, but small and positive, driving the accelerating expansion of the universe that has been measured by observations of distant supernovae. The value of the cosmological constant that we measure is extraordinarily small compared to what quantum field theory naively predicts it should be. The discrepancy between the theoretical expectation and the observed value is approximately 120 orders of magnitude, which is to say 10 raised to the power of 120 times larger than what we observe. This is, by any measure, the worst quantitative prediction in the history of theoretical physics. Something is cancelling the cosmological constant almost perfectly, leaving only the tiny residual we observe, and nobody knows what that something is or why the cancellation is so nearly exact. But here is where the anthropic principle enters with genuine explanatory force. If the cosmological constant was significantly larger than its observed value, the universe would have expanded so rapidly in its early history that matter could never have clumped together under gravity to form galaxies. No galaxies means no stars. No stars means no heavy elements. No heavy elements means no rocky planets and no organic chemistry. No organic chemistry means no biology. No biology means no observers. A universe with a large cosmological constant is a universe that nobody observes, not because such a universe does not exist, but because the conditions it produces are incompatible with the existence of anyone capable of measuring its cosmological constant. In an inflationary multiverse containing a vast range of bubble universes with different values of the cosmological constant distributed across the string theory landscape, we should not be surprised to find ourselves in one of the rare bubbles where the cosmological constant is small enough to permit structure formation. It is not that the value was designed for us. It is that we could not find ourselves anywhere else. This argument was made explicitly by Steven Weinberg in 1987, years before the accelerating expansion of the universe was directly observed. Weinberg used the anthropic principle within the multiverse framework to predict that the cosmological constant, if it existed and varied across the multiverse landscape, should be small but not zero. Because zero is not the only value consistent with structure formation. It should be the largest value consistent with the formation of the kinds of galaxies that eventually produce observers. When the cosmological constant was measured observationally in 1998 and found to be small but non-zero, the result was widely regarded as a striking, if controversial, success for the anthropic reasoning that Weinberg had applied. It was, in the judgment of many physicists, evidence that the multiverse was not merely a theoretical excess, but a framework with genuine predictive content. The formal distinction between the weak and strong versions of the anthropic principle is worth establishing carefully, because the two versions carry very different implications and are frequently confused with each other in popular discussions. The weak anthropic principle, in the formulation given by Brandon Carter in 1973, states simply that what we observe must be compatible with our existence as observers. This is a statement about selection, effects. It does not claim that the universe was made for us. It does not claim that our existence was in any sense necessary or intended. It claims only that any observation we make is automatically filtered through the requirement that we exist to make it. This is logically unassailable. It is a fact about the structure of observation, not a claim about the structure of the universe. The weak anthropic principle in this sense is modest, defensible, and genuinely useful as a tool for understanding why we observe the specific physical environment we do. The strong anthropic principle is a different and far more controversial claim. It asserts not merely that the universe must be compatible with observers, but that the universe must, in some stronger sense, produce observers. Some versions suggest that the constants of physics were necessarily tuned to permit life. Others invoke the participatory universe picture, associated with John Archibald Wheeler, in which observers play a constitutive role in bringing physical reality into definite existence through the act of measurement. The strong anthropic principle shades rapidly into metaphysics and theology, and most physicists who invoke anthropic reasoning in their work are careful to confine themselves to the weak version. The strong version is not required for the arguments that matter here, and introducing it would complicate rather than clarify what the physics actually demands. What the weak anthropic principle tells us, applied carefully within the context of eternal inflation and the string theory landscape, is that the fine-tuned features of our universe are not evidence of design. They are evidence of selection. We should expect to find ourselves in a universe where the cosmological constant is small, where the ratio of the electromagnetic force to the gravitational force falls within the narrow range that permits stable atomic structure, where the mass of the Higgs boson is close to the value that allows the chemistry of carbon-based molecules to operate. Not because these values were chosen for us, but because they define the boundaries of the set of universes in which we could possibly be asking the question. The multiverse in this picture is not a philosophical indulgence. It is the framework that makes the weak anthropic principle a genuine explanatory tool rather than a circular tautology. Without the multiverse saying that we must observe a life-permitting universe because otherwise we would not be here is vacuously true. With the multiverse, the same reasoning becomes a substantive prediction about the distribution of physical constants across the landscape of existing universes. This is the anthropic principle at its most useful and most defensible. It is a filter that explains, in principle, why observers like us find themselves in a universe with the properties ours has. And for several decades after Weinberg's 1987 paper, it seemed like a conceptually clean and scientifically productive way to make sense of the multiverse's bewildering range of possible physics. But then, physicists began to look more carefully at what the filter actually admits. Not what it excludes, but what it allows through. And what they found was deeply uncomfortable. The anthropic principle says that observers can only exist in universes compatible with their existence. It does not say anything about what kind of observers those must be. It specifies a necessary condition for observation to occur, but leaves entirely open the physical mechanism by which that observation is realized. And this is where the Boltzmann brain problem cuts through the anthropic framework with surgical precision. A Boltzmann brain is, by definition, a conscious observer. Whatever it is that makes a physical system count as an observer, a Boltzmann brain satisfies that criterion. It is a configuration of matter that supports subjective experience, at least momentarily. It processes information. It encodes something that functions from the inside as the experience of perceiving a world. The anthropic filter does not exclude Boltzmann brains. It cannot exclude them. Any universe in which random thermal fluctuations can spontaneously assemble, a Boltzmann brain is a universe compatible with the existence of an observer. The filter lets Boltzmann brains through just as freely as it lets evolved biological observers through. More freely, in fact, because, as we have already established, the probability of producing a Boltzmann brain through thermal fluctuation is incomparably larger than the probability of producing an evolved observer through the long chain of ordered physical processes that biology requires. This means that the anthropic principle, far from solving the Boltzmann brain problem, is part of what generates it. The logic runs as follows. We invoke the anthropic principle to explain why we find ourselves in a universe compatible with our existence. But in an infinite multiverse, the set of universes compatible with our existence as observers includes, in addition to the ordered, low entropy, life-permitting bubble we inhabit, an infinite number of configurations in which Boltzmann brains spontaneously fluctuate into existence in otherwise disordered environments. Those configurations are compatible with observer existence by exactly the same criterion as our own universe is, and they are produced far more abundantly. Therefore, within the multiverse, the anthropic filter selects for Boltzmann brains more strongly than it selects for evolved observers like us. The most probable observation consistent with being an observer is the observation of a Boltzmann brain, not the observation of a physicist in a well-equipped laboratory, surrounded by a consistent and historically continuous physical world. If this argument is correct, then the anthropic principle does not explain why we are here. It explains why a Boltzmann brain is here, and we happen, improbably, to be something more elaborate than that. The principle intended to resolve fine-tuning problems has itself produced a fine-tuning problem of extraordinary severity, explaining why we are the particular kind of observer we appear to be, rather than the far more common kind that the multiverse's statistical structure predicts, requires exactly the sort of elaborate justification that the anthropic principle was supposed to make unnecessary. The cosmologist Don Page has examined this problem with particular rigor. Page, who worked with Stephen Hawking at Cambridge and has spent decades thinking carefully about the foundations of cosmology and quantum mechanics, has argued that the Boltzmann brain problem represents a genuine crisis for any cosmological model that combines the anthropic principle with an infinite or eternal background. His calculations, using standard statistical mechanical arguments applied to the long-term evolution of de Sitter space, the kind of exponentially expanding vacuum that our universe appears to be settling into as its cosmological constant increasingly dominates its energy budget, suggests that the total number of Boltzmann brains produced in the infinite future of our universe alone, even without invoking the full inflationary multiverse, may exceed the total number of evolved observers by an astronomically large factor. The calculations are sensitive to assumptions about what counts as a Boltzmann brain and how to model the fluctuation rate, but the qualitative conclusion appears robust across a wide range of assumptions. Boltzmann brains dominate. Andreas Albrecht and Lorenzo Sorbo have independently examined the problem and arrived at similar conclusions, arguing that de Sitter space, the mathematical description of a universe dominated by a positive cosmological constant and expanding exponentially, is a fundamentally Boltzmann brain-generating environment when allowed to evolve for sufficiently long times. Because our universe appears to be asymptotically approaching a de Sitter state as the cosmological constant comes to dominate over matter and radiation, this means that the future evolution of our own observable universe is predicted to produce Boltzmann brains in numbers that, over the infinite future that de Sitter space permits, will ultimately dwarf the total population of evolved observers that our universe has generated or will generate during the brief stellar era. The brief stellar era. That phrase deserves to sit for a moment. The entire history of stars in our universe, from the formation of the first generation of massive stars, a few 100 million years after the Big Bang to the death of the last red dwarfs, tens of trillions of years from now, occupies a finite window of cosmic time. Before the stars, conditions were too hot and chaotic for complex chemistry. After the stars, the universe will grow cold and dark, the matter will disperse, the black holes will eventually evaporate through Hawking radiation on timescales measured in numbers, with more digits than there are atoms in the observable universe, and the universe will settle into a de Sitter equilibrium that it will then inhabit essentially forever. The stellar era, during which the conditions for biological evolution exist, is a brief, bright anomaly in an otherwise dark and nearly featureless cosmic history. The Boltzmann brain era, during which the universe's infinite future in de Sitter space produces random conscious fluctuations at a steady, if extraordinarily slow rate, is effectively eternal. And eternity, as always, wins the numbers game. The anthropic trap, as it deserves to be called, has two jaws. The first jaw is the fine-tuning problem it was designed to address. Without the anthropic filter, the extraordinary precision of the universe's physical constants demands an explanation that physics alone has not provided. The multiverse plus anthropic selection offers a framework for understanding why we observe fine-tuned constants without invoking design. This is the jaw that opened first and that drew physicists into the framework. The second jaw is the one that closed on them afterward. Having invoked the multiverse to explain fine-tuning through selection effects, physicists found themselves committed to a framework that generates Boltzmann brains in vastly greater numbers than evolved observers, and that uses the same anthropic filter to explain both. The trap does not merely fail to close after admitting the unwanted guests. It positively invites them in by the same door through which the wanted ones entered. Some physicists have attempted to modify the anthropic argument to exclude Boltzmann brains by requiring that the selected observer be not merely any conscious entity, but a specific kind of ordered observer with a reliable cognitive history. The argument is that science requires not just consciousness, but accurate perception, that the kind of observer relevant for scientific reasoning is one whose memories and observations correspond to real events in a real external world, and that Boltzmann brains, whose memories are structurally false, do not satisfy this more demanding criterion. This is sometimes called the full anthropic principle, or the self-sampling assumption, applied with a more restrictive reference class. The problem with this move is that it appears to beg the question. If you define the relevant class of observers as those with genuine histories and reliable memories, then of course you select for evolved observers over Boltzmann brains. But the definition is doing all the work. You have not solved the problem. You have simply stipulated it away by changing the scope of the anthropic filter. And any time a scientific argument rests entirely on a stipulation about what to count, rather than on a physical mechanism that explains why the stipulated criterion is satisfied, the argument has substituted verbal precision for physical content. The Boltzmann brain problem does not dissolve under this treatment. It retreats to a different level of the argument, where it reasserts itself as the question of why the physical mechanism of our universe should be expected to produce observers of the reliable kind rather than the unreliable kind, which is precisely the question it posed from the beginning. There is a version of the anthropic argument that attempts to address this more directly, and it is worth examining because it is more honest about what the problem requires. The argument appeals to the notion of self-locating belief. If you are an observer embedded in an infinite multiverse, and if you are trying to reason about what kind of observer you most probably are, you should assign probabilities to different observer types in proportion to how commonly each type is produced. This is called the self-sampling assumption in its naive form. Under this assumption, as we have seen, the probability that you are a Boltzmann brain is overwhelmingly large. So large that it is essentially certain. But some philosophers and physicists have argued for a different sampling rule called the self-indication assumption, which weights observer types not just by their frequency, but by some measure of their causal or computational complexity. Under this rule, a Boltzmann brain, which instantiates only a momentary and structurally impoverished form of experience, might receive a lower probability weight than an evolved observer with a rich, continuous, causally grounded history. The argument is that more complex or more informationally rich observers contribute more to the observer-generating capacity of the universe, and should therefore receive greater weight in any anthropic accounting. This argument is creative, and it may ultimately point in the right direction, but it carries a significant philosophical burden. It requires choosing a specific measure, a specific way of weighting different observer types, that is not derived from the underlying physics, but is instead imposed from outside as an additional assumption. The choice of measure is not innocuous. Different choices give radically different predictions about what kind of observer we should expect to be. And there is currently no physical principle, no equation, no experimental result that tells us which measure is correct. We are, in effect, adding a free parameter to the theory in order to make it predict the thing we already know, that we appear to be evolved observers rather than random fluctuations. That is not a solution to the Boltzmann brain problem. It is a parameterization of our ignorance about it. What the anthropic principle reveals, when examined honestly in the context of the multiverse and the Boltzmann brain problem, is a tension at the very heart of how physicists have tried to make sense of a cosmos too large and too varied for ordinary scientific reasoning to handle comfortably. The principle was invoked to explain why we see a fine-tuned universe. It was intended to transform an apparent miracle into a selection effect. And in that limited goal, it has had genuine success, most strikingly in Weinberg's prediction of a small positive cosmological constant. But the same reasoning that makes it powerful as a tool for explaining fine-tuning makes it impotent as a tool for explaining why we are the particular kind of observers we seem to be. The filter that explains our universe cannot explain our nature. The very framework built to make our existence comprehensible has generated a prediction that our existence, as a particular kind of ordered, embedded, evolutionarily derived consciousness, is statistically extraordinary in a way that the framework itself cannot account for. This is the anthropic trap in its full form. The tool that was supposed to make our existence comprehensible has generated a prediction that our existence, as a particular kind of reliable and historically continuous consciousness, is the statistical exception rather than the rule. And a framework that cannot explain why its own observers are the kind of observers capable of building it is a framework in a very specific and very serious kind of trouble. The full weight of that trouble, and what it means for every measurement ever made in the name of cosmology, demands a reckoning that the inflationary multiverse, for all its mathematical power, has not yet been able to provide. There is a particular kind of scientific failure that is far more disturbing than an experiment producing the wrong result. An experiment that contradicts a theory is a problem, but it is a manageable problem. You revise the theory. You find the missing term. You look for the flaw in the experimental setup. The machinery of science is built precisely to handle that kind of failure, and it handles it well. The history of physics is a long sequence of theories being broken and rebuilt, each iteration sharper and more accurate than the last. This process works because it operates on a foundation that nobody questions. The foundation that the experiment was real, that the measurements recorded mean something, that the physicist conducting the experiment is a genuine observer embedded in a genuine physical world, whose memories of previous results correspond to events that actually happened, and whose reasoning faculties are tracking something true about the structure of reality rather than generating noise. The more disturbing kind of scientific failure is the kind that attacks the foundation itself. Not the theory sitting on top of the foundation, but the foundation. The kind of failure that does not merely say your calculation was wrong, but says the calculator cannot be trusted. The kind that does not merely challenge a model, but challenges the conditions under which any model could be evaluated. This is the kind of failure that the Boltzmann brain problem, combined with the full implications of the multiverse, threatens to inflict on modern cosmology. And understanding exactly how it does that, and why the physicists who take it seriously regard it not as an amusing philosophical puzzle, but as a genuine and urgent empirical crisis, requires us to look carefully at the structure of the problem in its most rigorous form. Begin with what physicists call the typicality assumption. This assumption is not usually stated explicitly, because it is so fundamental to scientific practice that stating it feels redundant. The assumption is that we are typical observers, not special, not selected by any mysterious principle from among a distribution of possible observers, not occupying a privileged position in the history or geography of the universe, just average, ordinary members of the reference class of observers that our physical theories predict should exist. The typicality assumption is what licenses the step from observation to inference. If you observe a particular feature of the universe, and your theory predicts that typical observers should observe that feature, the agreement between observation and prediction constitutes evidence for the theory. That is the basic logic of empirical science. It works only if you are justified in believing you are typical. But in a multiverse that produces Boltzmann brains in numbers that overwhelm the population of evolved observers, the typicality assumption breaks down catastrophically. A typical observer in the full extent of the multiverse is not an evolved physicist. A typical observer is a random thermal fluctuation with a lifetime measured in fractions of a second. A structurally false set of apparent memories and no genuine history. If that is what typical means in the full distribution of observers that the theory predicts, then invoking typicality to connect your observations to your theory does not support the theory. It undermines it. The observation that you appear to be an evolved physicist embedded in a coherent physical world is not evidence that the multiverse is the right framework. It is evidence that you are among the extraordinarily atypical observers that the framework produces, for reasons that the framework itself does not explain. This is the internal contradiction at the heart of the Boltzmann brain problem. The multiverse framework, applied honestly, predicts that almost none of its observers are reliable. But the only evidence we have for the multiverse framework comes from observations made by observers who assume they are reliable. If the framework's own predictions undermine the reliability of those observers, the evidential base for the framework dissolves. The theory is eating the observations that support it. This is not a flaw in a single equation or a gap in a single argument. It is a structural collapse of the relationship between theory and evidence that defines what it means to do empirical science. Sean Carroll, one of the most articulate and careful thinkers in contemporary theoretical cosmology, has described this situation with characteristic directness. A cosmological model that predicts Boltzmann brains outnumber ordinary observers is cognitively unstable. It cannot be consistently believed. If you believe the model, you should believe that you are most probably a Boltzmann brain. If you believe you are a Boltzmann brain, you should believe your memories of the model are structurally false and your reasoning about it is unreliable. If your reasoning about it is unreliable, you have no basis for believing the model. The belief destroys its own foundation. You cannot occupy the position of believing it without simultaneously undermining the rational grounds for believing it. Carroll has argued, on this basis, that any viable cosmological theory must be constructed in such a way that it does not produce a Boltzmann brain-dominated universe. The absence of Boltzmann brain domination is not merely a desirable feature of a theory. It is a necessary condition for any theory to be self-consistent as a scientific claim. This demand places extraordinary constraints on cosmological model building. It means that any theory which combines eternal inflation with the standard thermodynamics of de Sitter space, which is precisely the combination most naturally suggested by current observations, is in danger of failing the self-consistency test unless it contains some mechanism that suppresses the long-term production of Boltzmann brains before they come to dominate the observer population. Several such mechanisms have been proposed. Vacuum decay. The possibility that our universe's current quantum vacuum state is metastable and will eventually tunnel to a lower energy state could in principle terminate the de Sitter era before Boltzmann brain production becomes catastrophic. If our universe is destined to undergo vacuum decay on a timescale shorter than the timescale for Boltzmann brain dominance, the threat could be avoided. But this requires a specific relationship between the vacuum decay rate and the Boltzmann brain production rate that is not guaranteed by the underlying physics, and that introduces a new fine-tuning problem in place of the one it solves. Another proposed mechanism involves modifications to the dynamics of eternal inflation itself. Some physicists have explored whether alternative inflationary models with different potential energy landscapes for the inflaton field could produce a multiverse with a finite rather than infinite total measure of observer-containing regions, thereby rendering the ratio of Boltzmann brains to evolved observers finite and potentially less than one. These explorations have been technically sophisticated, but have not produced a definitive solution. The inflationary framework is robust enough that suppressing its eternal character without sacrificing the observational successes of inflation turns out to be extraordinarily difficult. Every modification that prevents eternal inflation tends also to prevent the flatness and smoothness of the universe that inflation was invoked to explain. The deeper technical expression of this difficulty is what cosmologists call the measure problem. In ordinary probability theory, calculating the probability of an outcome requires knowing the total number of ways the outcome can occur, divided by the total number of possible outcomes. This requires both quantities to be finite or at least well-defined in the limit. In an eternally inflating multiverse, both the number of Boltzmann brains and the number of evolved observers are formally infinite. The ratio of two infinities is not defined by standard arithmetic. Different methods of regulating the infinities, different ways of taking a limit to make the counting well-defined, give different answers. Some methods assign overwhelming probability to Boltzmann brains. Others can be constructed to suppress them. But there is no physical principle that unambiguously selects the correct method. The choice of measure is an additional input to the theory that the theory itself does not provide. This is a genuinely devastating situation. The measure problem means that the multiverse, despite making dramatic qualitative predictions about the existence of other universes and the distribution of physical constants across them, cannot make unambiguous quantitative predictions about what kind of observer is most probable. The prediction that matters most for the self-consistency of the framework, the prediction about whether evolved observers like us are typical or atypical, depends on a choice that the theory leaves undetermined. Until the measure problem is solved, the multiverse cannot answer its own most pressing empirical challenge. Alexander Vilenkin, one of the pioneers of eternal inflation who developed many of the mathematical tools used to analyze the inflationary multiverse, has spent decades working on the measure problem and has proposed several candidate measures, including the so-called pocket-based measure and the holographic measure. Each proposal has strengths and weaknesses, and none has achieved consensus acceptance. Andre Linde and his collaborators have explored different approaches, including the stationary measure, while Alan Guth's group developed the scale factor cutoff measure, each designed to regulate the infinities of eternal inflation in a way that produces sensible predictions. But the multiplicity of proposals, each technically sophisticated and each giving different answers, is itself a sign of how deep the problem runs. If the correct measure were clear from the physics, there would not be a dozen competing proposals. The measure problem is not a technical detail awaiting a clever calculation. It is a foundational gap in the framework. The anthropic principle, as we saw, was supposed to be the tool that made the multiverses infinite. Diversity scientifically manageable by selecting, from the full distribution of possible universes, the subset compatible with observer existence. But the measure problem means that even this selection cannot be performed without additional assumptions about how to weight different observers. The anthropic principle plus the multiverse plus a measure prescription produces predictions. But the measure prescription is not derived. It is chosen. And the freedom to choose the measure is, in effect, the freedom to choose the predictions. A framework with that much freedom is not making predictions in the scientifically rigorous sense. It is making choices that happen to be dressed in the language of prediction. Don Page has pushed this analysis further than almost anyone, bringing to bear both his expertise in quantum cosmology and his unusual willingness to follow arguments to their logical conclusions, regardless of how uncomfortable those conclusions are. Page has argued that the Boltzmann brain problem forces us to take seriously the possibility that our current cosmological model is simply wrong in a fundamental way. Not wrong in the sense of needing quantitative adjustment, wrong in the sense of being built on incorrect assumptions about the large-scale structure of reality. He has proposed modifications to the inflationary framework that would limit or eliminate the eternal character of inflation, cutting off the infinite future of de Sitter space before Boltzmann brain production can dominate. These proposals require significant departures from the standard model of cosmology, departures that introduce their own tensions with observation. But Page regards those tensions as preferable to the alternative, which is accepting a theory that predicts its own observers are almost certainly not what they seem to be. The philosopher Nick Bostrom has approached the same problem from the direction of anthropic reasoning and the theory of self-locating belief, developing a framework called the self-sampling assumption and examining its consequences for how observers in infinite universes should reason about their own typicality. Bostrom's analysis makes the problem structurally precise in a way that highlights its resistance to easy resolution. If you adopt the self-sampling assumption, you should regard yourself as a random sample from the reference class of all observers in your universe or multiverse. If Boltzmann brains dominate that reference class, you should assign overwhelming probability to being a Boltzmann brain. If you reject the self-sampling assumption and adopt a more restricted reference class, you avoid the Boltzmann brain conclusion, but you do so by fiat rather than by physics. The choice of reference class becomes the critical and unjustified step in the argument. Bostrom's work does not solve the problem, but illuminates with great clarity why it cannot be solved by informal appeals to common sense. The problem is not that the Boltzmann brain conclusion seems absurd. It is that the alternative, restricting the reference class, requires a principled physical justification that nobody has yet provided. What all of this converges toward is something that should be stated plainly. Our best current theories of cosmology, the theories that have made the most successful quantitative predictions about the observable universe, including the temperature fluctuations of the cosmic microwave background, the large-scale structure of galaxy distributions, the abundance of light elements, and the value of the cosmological constant, are theories that, when followed honestly to their logical conclusions, predict a universe in which the kind of observer doing the observing is almost certainly not what they appear to be. This is not a prediction at the margins of the theory. It is not an exotic edge case that only manifests under extreme conditions. It is a central implication of the framework that follows from, combining the standard ingredients of modern cosmology, eternal inflation, de Sitter equilibrium, and the thermodynamics of thermal fluctuations, with nothing more than straightforward statistical reasoning. The disturbing implication of the multiverse is therefore not merely that other universes exist, or that our universe is one of an infinite number, or that the constants of nature could have been different elsewhere. All of those implications are philosophically interesting, but scientifically manageable. They can be incorporated into a scientific worldview without threatening the practice of science itself. The truly disturbing implication is that the same framework which produces those conclusions also produces the prediction that the observer drawing those conclusions is, in all probability, not an evolved physicist with a genuine history, but a random fluctuation with a false one. The theory is undermining its own epistemological foundations. It is generating a conclusion that, if true, makes the theory itself unjustifiable as a scientific claim. This is not a paradox in the playful sense, an amusing contradiction that resolves itself with a clever insight. It is a paradox in the serious sense, a genuine logical instability at the core of our most ambitious attempts to describe the full extent of physical reality. Now, sit with the full weight of what this means for the practice of science. Every measurement ever made in physics rests on the assumption that the person making it is a reliable observer. Every galaxy catalogue compiled by generations of astronomers. Every particle collision recorded at the Large Hadron Collider. Every supernova spectrum that revealed the accelerating expansion of the universe. Every photon from the cosmic microwave background that confirmed the predictions of inflation. All of it was recorded by observers who assumed their instruments were working, their memories were accurate, and their reasoning was tracking something real. That assumption is not a trivial one. It is not a background condition that can be taken for granted, regardless of what the physics says. It is a substantive claim about what kind of entity the observer is. And if the physics says that most observers are not the reliable kind, the assumption is not automatically justified. It requires defense. It requires a physical account of why this particular observer, the one making this particular measurement, belongs to the rare class of reliable ones rather than the overwhelmingly common class of random fluctuations with false histories. No such physical account currently exists within the multiverse framework. And the absence of that account is not just a gap in our knowledge, it is a gap in the very structure of the theory that makes the Boltzmann brain problem different in kind from other unsolved problems in physics. Most unsolved problems in physics are problems of incomplete knowledge. We do not know what dark matter is made of. We do not know how to reconcile general relativity with quantum mechanics at the Planck scale. We do not know what drove the asymmetry between matter and antimatter in the early universe. These are genuine and important gaps, but they are gaps in our description of what exists. They do not threaten the reliability of the observations that identified them as gaps. The Boltzmann brain problem is different. It is a gap in our ability to trust any description at all because it attacks the observer rather than the observed. This is why the problem matters beyond its immediate technical context. It is a symptom of something deeper, something that the construction of the multiverse has exposed rather than created. The assumption of observer typicality has always been foundational to science, but it has never previously been directly threatened by the theories it supports. In the pre-multiverse era of cosmology, the observable universe was the totality of what physics described, and within that, totality-evolved observers were the only kind of observer the theory countenanced. Typicality was automatically satisfied. But in the multiverse era, the theory extends its claims to a domain incomparably larger than what any observer can see, and in that extended domain, the statistical distribution of observers does not support the typicality of the kind doing the extending. The theory has grown large enough to undermine its own foundations. Probability itself fractures under the pressure of the multiverse. In a finite universe, probability is a well-defined quantity. You can, in principle, enumerate possibilities, count outcomes, and assign frequencies. In an infinite multiverse, the standard rules of probability no longer apply without modification, and every modification introduces assumptions that the theory does not justify. The question of whether it is probable that you are an evolved observer rather than a Boltzmann brain cannot be answered within the existing mathematical framework of eternal inflation. It requires a solution to the measure problem. The measure problem has been open for 4 decades. The most careful workers in the field have not converged on a solution. This is not a problem on the verge of resolution. It is a problem whose difficulty appears to be fundamental rather than technical. And yet, the observations keep coming. The measurements keep accumulating. The cosmic microwave background satellites keep mapping the sky with extraordinary precision, and their results keep matching the predictions of inflation with extraordinary accuracy. The framework that generates the crisis also generates the best quantitative account of the observable universe that physics has ever produced. This is the most disorienting aspect of the situation. The theory is right and possibly self-defeating simultaneously. Its successes are real. Its failure, if it is a failure, is not in its predictions about what we can see, but in its predictions about what we are. This places cosmology in a genuinely unprecedented position. It is a field whose most successful theoretical framework may contain, at its logical core, a prediction that the theorists developing it cannot be trusted to be the kind of observers whose reasoning about the framework is reliable. Every paper written on eternal inflation, every calculation performed on the string theory landscape, every anthropic argument deployed to explain the cosmological constant, was produced by an observer who assumed, without being able to justify the assumption from within the framework, that they were the kind of observer whose scientific work was tracking something real. If the framework is right about Boltzmann brains, the work is not tracking something real. If the work is tracking something real, the framework is wrong about Boltzmann brains. Both possibilities are disturbing. The first destroys science. The second demands a revision of our best cosmological theories, whose scope and depth we cannot yet foresee. The multiverse was not supposed to end here. It was supposed to be the explanation that made everything else comprehensible. The fine-tuning of physical constants, the silence of the sky, the peculiar suitability of our universe for complexity and life, all of those were supposed to become less mysterious once the multiverse was accepted as the framework within which they resided. Selection effects would do the work that design could not. The anthropic principle would replace miraculous coincidence with statistical inevitability. The universe would turn out to be one of many, and its peculiarities would dissolve into the overwhelming diversity of what exists. Instead, the multiverse has produced a disturbing implication that its architects did not anticipate, and that its most careful proponents cannot resolve. In a cosmos large enough, old enough, and quantum mechanically branched enough to make the anthropic filter scientifically useful, the same properties that make it large enough also make it a factory for observers whose reliability is structurally compromised. The most common conscious entity in a multiverse governed by the laws of physics as we understand them is not a civilization. It is not a species. It is not a mind shaped by 4 billion years of evolutionary pressure into something genuinely fitted to perceive and reason about the world it inhabits. It is an accident. In the full accounting of what exists, the evolved physicist sitting at a desk is not representative of what consciousness looks like across the multiverse. The Boltzmann brain is, and that single conclusion, following with mathematical necessity from frameworks built on confirmed observations, is what makes the problem not merely philosophically uncomfortable, but scientifically urgent. This is what our best science currently tells us, when we have the honesty to follow it all the way. Not a comfortable version of it softened at the edges. Not a version that quietly omits the parts that refuse to resolve. The full version. The one that begins with Alan Guth solving the flatness problem in 1980 and ends through a sequence of logically connected steps that nobody designed and nobody wanted, at the question of whether the person following those steps can trust their own mind. The question is not resolved. It may not be resolvable within the current framework, but it is real, it is rigorous, and it is among the most important questions that physics has ever been forced to take seriously. Because it is the question that sits beneath all the others, beneath every measurement and every model and every confident claim about the structure of the cosmos. It is the question of whether the observer at the center of all scientific knowledge is what they appear to be. Whether the mind that builds the theories is genuinely embedded in the reality those theories describe. Whether the universe that physics has spent 4 centuries learning to read is a universe that produced, in us, something capable of reading it honestly. The unsettling truth is that we do not know. We assume. We have always assumed. And for most of the history of science, that assumption was safe, because nothing in the physics threatened it. Now something does. The same equations that describe the birth of our universe, stretched honestly to their full extent, describe a cosmos in which that assumption is almost certainly false for most of its observers. We are left with a choice that is not really a choice, because we have no alternative but to continue. We continue to observe. We continue to measure. We continue to reason. We continue to build theories and test them and revise them. We do all of this while holding, at the back of our minds, the possibility that the framework within which we do it has generated a prediction about us that we cannot dismiss, cannot verify, and cannot afford to simply ignore. The multiverse has a disturbing implication. Not that reality is larger than we thought. Not that other universes exist with different laws and different histories. Those implications are surprising, but they are not threatening. The disturbing implication is smaller and more intimate than all of that. It is the implication that in the full accounting of what exists, you are probably not what you think you are. That the experience you are having right now, the sense of continuity in history and reliable perception, is almost certainly the exception rather than the rule in the total distribution of conscious experience across the cosmos. That most minds, in the fullest and most honest sense that our physics allows, do not have a yesterday. And the most disturbing part of all is not that the implication might be true. It is that we built the framework that produced it from observations we trusted completely, using reasoning we believed was sound, in pursuit of a theory we hoped would finally make everything clear. We followed the physics all the way to the edge. And at the edge, the physics looked back and told us something about ourselves that we are not equipped to verify and not able to forget. That is what it means to take the multiverse seriously. Not the wonder of infinite worlds, the weight of the question they force upon the only world you have ever known. The question of whether knowing is something you are actually doing, or something that only feels, from the inside, like it is.